Hi, everyone. I wanted to share a couple of additional videos. These videos will show some cool tricks in R if you are progressing through your final project and want to try some of these out on the final project, go for it. I hope that these can be useful to you. So one thing that affects me a lot is that sometimes our data isn't perfect for analysis. For example, many variables are called count variables, while some values, like a political polarization score, can have negative and positive values, or like temperature can have negative and positive values. Others don't have negative values. Others just have positive values. So, for example, crime rates can only be positive. There's no such thing as a negative crime rate. That would be like crossing the street to help someone, and somehow that gets counted as a negative crime, So we don't do that. We just have positive crime rates. The same thing is true for any count variable. For example, coffee cups, corgis, births, deaths, awards. Any of these things are count variables. You can have 1, 2, 3, 4, 5, a million of them, but you can't have negative one. There's no such thing as a negative corgi. And we can actually prove this. We can visualize it. So I'm going to take, in about 2 minutes, I'm going to show you how this works and visualize it. For example, I like to use the Japanese municipalities data because it has great crime rate data between 1980 and 2017. The crime rate's actually, yeah. So here we go. I'm running it in this script right here, which is also going to be posted to Blackboard. And great. So you can see that I've downloaded it here. JP, the name of our data set now, has been uploaded here, and we can glimpse it real quick. I might glimpse it again so that it comes out a little better. Okay, there's a lot of stuff in here. Holy moly. We've got a municipality. So, okay, Sapporo in this city in Hokkaido. It has a municipality code. It has a year. It has a population. It has a crime rate right here. Okay, and I think it also has an income per capita right there. Okay, great. And we've got that for all of these towns. So let's visualize the crime rates over time within this data frame. Boom. Okay. And it looks like there aren't really any negative values, right? Proof. We can have a crime rate of 0. We can have a crime rate of 1 million. Crime rates, by the way, are usually like their counts divided by population. So still same issue, no negative values. Here's the problem. One last thing. You can also notice that this is pretty right skewed. The tail goes out to the right. That is very, well, that's the case for all count variables. It's like they want it to be a normal distribution, but then they got cut off right at the beginning. So they're always going to be pretty right skewed. So the problem is if we model crime rates as an outcome variable, linear regression might give us a best fit line that includes negative outcome predictions. And that's kind of weird, right? That would say that our best fit line is predicting, sometimes you'll get negative crime. That should make you doubt that model. That is a weird model. That is a weird best fit line, right? So, for example, if we run M, we don't really care about the beta coefficients in this case, but we could just be interested in grabbing the fitted values. The fitted values are the values along the line. They are our Y predicted values, right? And so I'm going to put them into the data frame. I'm going to call them predicted. I'm going to also grab from the model table, our crime rates. So I'm going to grab back out of the model the data that we put into it so that we can compare Y predicted and Y observed. And then last but not least, I'm going to filter just to the rows where the predicted values are negative, where they're less than 0. So let's see what that looks like. Okay, so I ran the code. I'm going to pull this up so we can see it. All right. Wow. So when our crime rate is 2.57, when the actual observed one is, sometimes we predicted it to be less than 0. A lot of times we predicted it to be less than 0. It seems like if we ever had a pretty low crime rate, we predicted it to actually be less than 0. And sometimes this gets pretty bad, like a crime rate of 6 can be a full 10 points off, a full 4 points into the negatives. So that's not really great. We don't like that. That best fit line probably doesn't represent reality very well. It probably predicts the high values very well, but it doesn't predict the low values of crime very well. So there is a cool trick of statistics we can use to get around this. We can transform our variable. What does that mean? When you transform a variable, in this case, you use some mathematical process. You apply it equally to every single row in the data. That way, the entire variable changes, but it all changes consistently. So it's systematically different. Not each row is equally different, you could say. Okay, so one way that we do this is by taking the log of a variable. Log transformations are really helpful for count variables because they can take any positive value and stretch it out on a negative to positive scale. So if you had values from like 0 to 100 and they were right skewed, it's going to stretch it out and the distribution will actually become normal. It's going to stretch it out and change the values. So if we were to do this in our model, well, let's just try a couple things. First, we could use the mutate function to change the value of a variable. And if we did that, if we just tried to take the log of crime rates like I'm about to do, let's see what happens. It works, but if we really zoomed in, we would find that we had actually just created we would find that we have created some pretty weird values. That is to say, anytime that a 0 happens, if you take the log of 0, it's kind of like the divide by 0 problem, you know how the world explodes? Not good. You can't take the log of 0. It's unclear what it really means. So if you do that, you're not going to be able to model that data. It's going to feed R a value called NaN, and R doesn't know what to do with that. So instead, we can change it just a little bit. We can add a very, 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 very small number like this to crime rate and take the log of all of that. So that's going to shift all the values of crime rate just a little bit to the right? Just a little bit. And that means that a value of 0 is no longer going to be 0, it will be 0.00001 or something like that. And so when you take the log of it, it won't have the divide by 0 problem anymore. And so we could run that. And while we can't see it here, we'll see it in a moment. It's going to transform the variables. So let's check this out. We can run a second model that looks like this. And let's say we're predicting it with like population, income, and age, and the median age. Doesn't really matter where our predictors are, same problem. We've now made a new model. It's going to have different predicted values. It's going to have different crime rates. We can actually visualize those crime rates right now. These are technically log-transformed crime rates. You'll notice that the scale is no longer a right-skewed distribution from 0 to like 100, I think it was before. We can actually see. Yeah, this is what it was before, and this is what it looks like now. It's been stretched out and changed. So like this value is the highest value, but it's been altered a little bit. The values that were very close to 0 get really negative values. The values that are very, very, very high get a little higher values over here. The funny thing is our outcome variable is now fundamentally different. So we've solved the problem of negative predicted values, so our model will now be more accurate. But our coefficients are going to be different. So let's interpret the coefficients for this model. We can see the same kinds of outputs right here. So this tells me that as population increases by 1 person, the log of crime rates tends to increase by 0.000000271 log crimes per 1,000 persons. That's a crime rate. So it increases by a very small number of log crime rates. Interesting, right? We have to be careful to remember to report it in that way, because the effects that our model predicts are all going to be in that unit. Income per capita is going to be in those units. Age is going to be in those units. That is to say, like, as age increases by 1 year, you'll get about minus 0.05 log crime rates, or log crimes per 1,000 persons, okay? It's a weird way of saying it, but you might find that variables that weren't statistically significant before, maybe now they are. That's because we've modeled the data more accurately than we did before. This is a quick way to deal with count variables using linear regression. Down the road, there are also some specific kinds of regression models used to model count variables. Some of them are called the Poisson, the negative binomial, and gamma models. All of those are used to model variables where you can't have negative outcome values. But good news, we don't really need them. Not at the moment anyways. Log transforming our outcome is a really good quick fix that can help us use linear regression on count variables. This is only necessary if your outcome variable is a count variable. If one of your predictors is a count variable, go to town. Don't need to log transform. It'll be great. So if you're interested in using crime rates, we can talk about how you do this with your data. Thanks for tuning in and have a good one.